All right, so let's talk about something that's literally all around us, every single second, but we can't see it. I'm talking about the invisible world of gases. Today, we're going to use something called the kinetic theory of gases to kind of build a mental microscope to see what's really going on in the air we're breathing right now.
So let's just start with a simple question. I mean, look around the room you're in right now. The air, it seems totally still, right? Empty, calm. But what if you could zoom in like billions and billions of times? What would you actually see? Well, on one side, you've got what we see every day, right? A balloon, just floating there. Seems pretty simple. But then you look at the other side, and that's the microscopic reality. It's a wild, chaotic dance. You've got countless tiny particles just zipping around, bouncing off each other, hitting the walls, and that chaos, that's the very thing keeping the balloon inflated. Crazy, isn't it?
And this is the whole point, really. This microscopic world, it's just fundamentally different from ours. Seriously, it operates by a set of rules that feel completely alien to everything we see and feel in our day-to-day life.
Yeah, this quote just nails it, doesn't it? It gets right to the heart of the problem. Our intuition, our common sense, it just completely breaks down at this scale. Everything is way too small, way too fast, and the way things interact is, well, it's just plain weird. So you have to wonder, how on earth did scientists even begin to make sense of this crazy alien world?
Well, they did it by doing what humans do best. They imagined. They built a model. Not a physical model, but an idea. A set of rules that would let them predict how these invisible particles behave, even if they couldn't see them with their own eyes.
And what's so cool about this is that it wasn't some aha moment from a single person. No way! This idea was built over centuries. It started way back with philosophers in ancient Rome, like Lucretius, just thinking about it. Then, hundreds of years later, guys like Bernoulli and Maxwell started putting serious math behind it. And finally, in 1905, Einstein comes along and provides the definitive proof, the absolute smoking gun evidence. Think about that. It took us over 2,000 years to go from, I think this is happening, to, okay, we can prove this invisible world is real.
And all that incredible work, all those centuries of thinking, led to this, the kinetic theory of gases. And you know what's so beautiful about it? It's actually super simple. It boils everything down to one core concept. A gas is just a massive collection of tiny, tiny particles that are in constant random motion. That's it. So simple. But as we'll see, it's unbelievably powerful.
So if we think of this theory as a game, these are basically the rules. It's kind of like a game of 3D billiards playing out on a cosmic scale. First, you've got these super small particles with tons of empty space between them. Second, they're always moving, completely at random. Third, they're constantly crashing into each other and the walls of whatever container they're in. And fourth, these collisions are perfect. No energy is lost. That's really the whole shebang. And with just those simple rules, you can explain everything from how an airbag inflates in a split second to what holds up our entire atmosphere.
Okay, this next part, this is probably the single biggest insight to come out of the whole theory. It's something that completely changed how we think about a feeling we experience every single day. I'm talking about heat.
And you know, people have been wondering about this for a long, long time. Way back in 1620, a guy named Francis Bacon had this just incredible intuition. He suggested that heat wasn't some weird invisible fluid like people thought. He said it was, and I quote, motion and nothing else. And guess what? Hundreds of years later, the kinetic theory proved he was absolutely right.
Because this is literally what heat is. This simulation just shows it perfectly. Look over on the left. The temperature gauge is cranked up, and those little particles are just whizzing around like crazy. Now look at the right. The temp is low, and see how much slower they're moving? So that's the big takeaway here. Temperature isn't a thing, it's a measurement of the average motion, the average kinetic energy of all those particles. It's that simple. Hot just means fast, cold just means slow.
And this is the perfect bridge, right? It connects our world, the macroscopic, with their world, the microscopic. What you and I feel as temperature on our skin is really just the average speed of all those molecules hitting us. And what we measure as pressure, in a bike tire or whatever, that's nothing more than the combined force of trillions upon trillions of these tiny particles smacking against the inside of that tire every single second. It's incredible.
So the theory gave us the blueprint, right? The instruction manual for this invisible world. But now, in the modern age, we can take it a step further. We can actually use that blueprint to build ourselves a kind of virtual microscope and finally see it with our own eyes.
So we have the theory, right?
We have the rules of the game, all the physics equations that tell us how this microscopic world works.
But now, technology lets us actually see the game. Modern computers are so powerful they can simulate it all and let us watch it play out in real time. We can finally see the unseen.
And a fantastic tool for doing exactly that is something called the molecular workbench. Think of it like a virtual laboratory on your computer. All the fundamental laws of physics we've been talking about are programmed right into it, so you can actually see and even interact with atoms and molecules directly.
And what's so amazing about a tool like this is that it completely changes how you learn. It's not passive anymore. It becomes active. You're not just reading in a book that more heat means more pressure. No, you can literally grab a virtual slider, crank up the heat yourself, and watch those little particles start zipping around faster and smacking into the walls harder. You get to discover these fundamental relationships for yourself, just by playing around and experimenting.
Okay, so playing around in a virtual world is a fantastic way to learn, for sure. But why does mastering this invisible, kind of alien world matter so much anyway? Well, it's because these rules, these fundamental principles, they don't just apply to gases. They are the foundation of pretty much everything.
You know, the Nobel Prize winner Leon Letterman put it perfectly. And I love this quote. He said that atoms and molecules are basically 85% of physics, 100% of chemistry, and 90% of modern biology. I mean, it's so simple, right? If you can understand how atoms and molecules behave, you basically hold the key to unlocking almost all of modern science. And there's a name for this whole field of foundational knowledge. It's called SEAM. That stands for the science of electrons, atoms, and molecules. And the kinetic theory we've been talking about, that's a huge piece of the puzzle. SEAM is truly the bedrock that modern science is built on.
And you know, from that bedrock, we've built our entire modern world. I mean, just think about it for a second. Designing brand new materials, creating life-saving medicines, developing new kinds of clean energy, building the super-fast computer chips in the phone in your pocket. Every single one of those things depends entirely on our ability to understand, predict, and, well, manipulate things down at the atomic level.
Which kind of brings us to a final pretty mind-bending thought. For more than 2,000 years, the atomic world was something we could only imagine. But now we can simulate it. We can build and test things on an atomic scale right inside a computer long before we ever step into a real lab. So the question isn't really what can we build anymore? It's what will we build next? Where does all this take us?